I am Sudha Shrikant and this is my affiliation. Today's topic of my video is mutual coupling. How to deal with coils which are mutually coupled. There could be magnetic coupling, or there could be electrical connections because of which coils may be connected. How to deal with the induced EMFs, like how to evaluate the magnitudes, how to estimate the magnitudes, how to estimate the polarity of the EMF induced in coils. That is the topic of today's discussion. And I also deal with what we call as dot conventions, which are helpful in formulating equations in network analysis. So with this background, let us try to consider mutual coupling. Now I'll try to take a simple arrangement of let's say two coils which are placed on a core, a magnetic core. So I will try to write the structure by writing a core. A magnetic core would be, I would make it a nice rectangle. Okay. Let me draw. I'll copy this figure, then I'll paste it, reduce it in size. I'll take it like this. I've taken a simple magnetic core. I'll consider two coils which are wound on this particular arrangement, this former or a core. Let me imagine a coil which is wound in a clockwise direction on one of the limbs of this core. Most of the viewers can relate it to a transformer. Okay, this is one coil which is wound in the clockwise direction. I'm imagining another coil which is wound on the same core. I will wind it in the anti-clockwise direction. So let me keep the second coil, in this manner. Okay. All right. So these are the two coils that we have, which have been kept on this particular core. This is my core. This is the core. These are the two windings. All right. So let us try to have voltages applied to these coils such that currents result in these coils. Let us imagine the current I1 is made to flow the coil which is in yellow, and I2 is the current that is made to flow through the coil in pink. Okay, so we can easily see that one winding is in the clockwise direction, or the current that is flowing in yellow coil is in the clockwise direction, whereas the current in coil I2 is in the anti-clockwise direction or counterclockwise direction. We know from Fleming's right hand rule that the flux produced by the coil depends on the direction in which the current flows through the coil, isn't it? So if we extend that particular principle to these two coils, we are able to find out that the flux that is produced in the coil which is in yellow, if we can call that as phi1, it is going to be a clockwise flux. So I'll try to indicate the clockwise flux in yellow. This is phi1. Phi1 is the flux that is produced due to the current I1 which is flowing through the coil in yellow. All right. So if we can look at the other coil which is in pink, the current flowing is in the counterclockwise direction. So accordingly, if we extend the Fleming's right hand rule, then what we get the flux to be in this pink coil, it will be in this direction. It will be in this direction. This will be phi2. Okay, if we can see that phi1 and phi2 aid each other, they support each other because they're in the same direction. The resultant flux in the core is obviously the sum of phi1 and phi2. Or in other words, to put it simply, we say that the situation here is aiding flux, or flux being aiding each other. I'll put it this way: fluxes are additive, or we say they are aiding fluxes. They aid each other, aiding fluxes. Okay, you can see even the current flow through the coil in another way. We can indicate it by what we call as dots and crosses. You know, crosses are the places where the currents are supposed to be entering, or current entering points are indicated by crosses. These are the cross points. Currents are entering at this end, they are coming out at this end. So we can do this kind of representation also. So either ways it's all right. So we can show the direction of flow of current this way in the coil, or we can show by dots and crosses. Okay, dots would mean current coming out, crosses is current getting in. So this is another convention we have. Whatever convention we take, it means the same. Okay, so the current I1 here is flowing this way. That means it is getting inside here, it's coming on this end, coming out, getting in here, coming out here, getting in here, coming out here, and finally leaving the winding here. It's like this. All right, so phi 1 and phi 2, if we can see in these figures, they aid each other. Okay, so normally the windings are not shown. You know, the direction in which the windings have been placed on the core of the magnetic material is not shown. Instead, what we have is we represent it by what we call as dot conventions. Okay, so we will come to that later. So we will now see how the fluxes are subtractive, like opposing fluxes. How opposing fluxes are represented, we will try to consider the situation. Okay, I will try to copy or else let me draw the figure all over again. Okay, I will draw a rectangular former or a core. All right, I'll take the same one, I'll paste it and make it little smaller. Okay, I've drawn the core. Now suppose the two windings that are there, I'll take the same color. Let this winding be is in the same direction. Let it continue to be the same. Okay, I'm winding a clockwise winding is my yellow winding. Okay, the current through this winding, obviously I will call it as I1. Okay, so I1, this is the direction of flow of current, right? This is the direction of flow of current, or we can see that the current is entering inside, it is coming out outside, entering inside, coming out outside, this way, and this is how I1 leaves the coil. So I1 has got a point of entry and I1 has a point of exit. So if we look at this, so if you can hold the finger, your right hand finger, in such a manner that the fingers curl in the clockwise direction, then the thumb would be pointing upwards. That is your Fleming's right hand rule. So the flux that is pointing upwards would be like this. It will circulate in this direction. This is clockwise flux. All right. Now on the other hand, let us imagine that the pink winding that we were talking about in the previous case, instead of being wound in that manner, we will reverse the way it's wound. What I mean is, I will draw a line like this. Now I'll put the winding in this manner. All right. Now I'll pass the current I2. Let the current entry point be the same. So what's happening here is the current is coming out at this end. It is entering here, coming out here, entering here, coming out at this end, entering here. All right. Now if we look at this situation, how is the what is the direction of flow of creation of flux phi 2? So we may have to hold the fingers in such a manner that the thumb is now again pointing upwards, or in other words, the flux that is produced due to this current is in this direction, phi 2. All right. This is your Fleming's right hand rule. You have to hold the direction, if you have to hold the conductor in such a manner that your fingers are indicative of the flow of current. Then the thumb would be in the direction of flux. So if you can see, the fluxes phi 1 and phi 2 in this situation are opposing each other. Fluxes are opposing or subtractive. I'll put that word here. I'll make it subtractive, are opposing fluxes. So if these two coils are coupled mutually, obviously they are coupled because of the core, presence of the core. So we are imagining that the core is made up of magnetic material. Obviously there is mutual coupling between the two. What do we understand by mutual coupling? By the word mutual coupling, what we mean is the current in one coil is capable of producing voltage in the other coil. That is when we say that the coils are mutually coupled. If that is a situation, how do we compute the induced EMFs in the coils? That is the topic of discussion today. Okay, if this is understood, I will take you through another slide. I suppose this is visible, this is clear. We are talking about now mutually coupled coils. So we normally represent the coils in this manner. The coils are being shown like this. Coil 1 has got a self-inductance of L1 and coil 2 has got coefficient of self-inductance L2. And these two coils are coupled with what we call as a coefficient of mutual coupling M. Right? Now, what is the significance of these dots? That has to be properly understood. That is the objective of this video. That is the aim of this video. Okay, I want you people to understand how to interpret the dots. Alright, so we have different cases. If we can see here, case 1 deals with current entering the dots at both ends of the coil. We are talking about figure 1a. This is figure 1a. Okay, we don't exactly get to know whether the windings are in the clockwise direction or in the anti-clockwise direction. You don't get to know because the coil is very much kept inside the entire arrangement. If it is a transformer, a body covers it. You don't know whether the windings are in the clockwise direction or in the anti-clockwise direction. So instead, what you get to know is you get to see these dots. The polarity is displayed or depicted in the form of keeping dots. We are trying to make an effort to understand these dots. What do we exactly mean by these dots? What do they convey? That is what we are trying to see. Okay, so in case 1, if we look at the figure 1a, it's clear that current I1 is entering the dot of coil 1. Current I2 is also entering the dot of coil 2. They are simultaneously entering. We are talking about instantaneous currents. Current at any instant. At any instant, both the currents are entering the dots at their respective coils. That is a situation. Alright, so if this is a situation, then how do we consider the EMS induced in the coil? We are talking about the mutually induced EMF typically, because self-induced EMF we know how to compute. Self-induced EMF is very simple. Self-induced EMF in coil 1 for that matter can be written as L1 di1 by dt. Okay, EMF induced in the coil is basically L di by dt if it is an isolated coil. If it is a mutually coupled coil, in addition to the self-induced EMF, you may even have mutually induced EMF. Now our objective is to find out what is the magnitude of this mutually induced EMF and how do we consider its polarity. That is the idea. Alright, so having said that, let us go ahead with the description. So when the currents enter the dot, how to compute the magnitude? The magnitude is given by, if we talk about the magnitude of the mutually induced EMF in coil 1, if we have to consider that, the magnitude is given by the coefficient of mutual coupling and the rate of change of current in coil 2. Because this current will be producing an EMF in coil 1. That is why we say that they are mutually coupled. If that was not the case, we wouldn't have said they are mutually coupled. The very fact that we are mentioning that these two coils are mutually coupled, what we mean is the current through one coil will produce an EMF in the other coil, in the other mutually coupled coil. So obviously in coil 1 you have two EMFs, one due to L1, which is L1 di1 by dt. The other one is mutually induced EMF, which is due to the current I2. And the coefficient of mutual coupling is M. So, if you look at this slide, it's very clear that the magnitude of the mutually induced EMF in any one coil is equal to the coefficient of mutual inductance or mutual coupling times the rate of change of current in the other coupled coil. Alright. So in coil 1, you will have a mutually induced EMF due to I2. In coil 2, you have mutually induced EMF due to current I1. And the coefficient of coupling is M. That is what we mean. That is about the magnitude. The question is how to take the polarity. Polarity is determined by the position of the dots. Where are the dots present? In this case, the current, if you can see, is entering the dots. Our dots are present at current entry points. This is where current I1 is entering, and this is where current I1 is leaving. Current I1 is leaving the undotted end. Current I2 is also leaving the undotted end. I2 is also entering the dot. I1 is also entering the dot. This is very, very evident from the diagram itself or from the figure 1a itself. Now, if this is the case, how to determine the polarity? That according to dot convention, it indicates that the fluxes are aiding each other. They're additive fluxes. Hence, if the current enters the dot in any one coil, it will produce an EMF which is positive at the dot of the other coupled coil. Current I1 is entering the dot of coil 1. This current will produce an EMF in L2 which is positive at the dot. Where is dot? Dot is at the top of L2. So the top terminal is positive, the bottom terminal is negative. That's how we understand. Similarly, if we look at current I2 is also entering the dot. So according to dot convention, this I2 will produce a mutually induced EMF whose magnitude is M di2 by dt, which is positive at the dot of the coupled coil. Dot of the coupled coil is L1, which is the dot is at the top. So obviously you will get a top end to be positive. We can represent it as a dependent source. Okay, controlled source. Why it's a controlled source? There again it is very simple, because your M di2 by dt or M di1 by dt, they are dependent on the currents I1 and I2. So that is where the dependency come. And these sources are voltage sources. They are current dependent voltage sources. We have typically taken an example of, if you take an example of a transformer, or in this particular situation where we are showing current I1 and I2, we say that they are current dependent voltage sources. Right? This situation is current dependent voltage sources. Hence I have taken the dependent source representation. You can write it this way, or you can simply write the equations. So this way it becomes easy for someone who is little, want to be little more clear, go step by step. So one can represent it this way. This is how we decide the polarity of this situation wherein the current is entering the dots of both the coils. Okay, so this is flux aiding, additive fluxes. The field produced by one coil will support the field produced by the other coil. Okay, let us try to talk about the other situation. What is this situation? Okay, here look at the situation. In this particular case, current I1 is entering the dot of coil 1, whereas current I2 is leaving the dot of coil 2. Okay, it is I2 is entering the undotted end, it is leaving the dotted end, whereas I1 is entering the dotted end, leaving the undotted end. They are opposing fluxes. They produce opposing fluxes. So if this is the situation, how to understand the polarity or how to get the polarity with dots? If this is the situation, how to take the polarity? So according to the dot convention, the magnitude of the mutually induced EMF in any one coil is equal to the coefficient of mutual inductance times the rate of change of current in the other coupled coil. The magnitude is simple. We need not have to worry too much about the magnitude. Magnitude is simple to understand, right? So if the two coils are coupled, in coil 1, if you get an EMF due to the current in the other coil, that is I2, you call that to be a mutually induced EMF. So the magnitude of mutually induced EMF is M di2 by dt in coil 1. This is our coil 1. Similarly, in coil 2, the mutually induced EMF magnitude is M times the rate of change of current in coil 1, that is I1. Alright, it is in coil 2, but the current of coil 1 is producing an EMF. That's why you say it is a mutually induced EMF. Alright, that is about the magnitude. Now how to understand the polarity? The polarity again is simple. Okay, what is of polarity? Current I1 is entering the dot. We just now saw if the current enters the dot, it will produce an EMF which is positive at the dot of the other coupled coil. Right? So current I1 is entering the dot. Other coupled coil has got a dot at the bottom. So at the bottom end, you put a plus sign. And the other end is negative. Alright? It is that way. Now, if we look at I2, I2 is leaving the dot. If I2 leaves the dot, then the dotted end of the other coil is negative. Dotted end of the other coil is, the top end is dotted. So this is negative and this is positive. That is an interpretation. That is how you interpret the dots. The interpretation of dots is done this way. Alright, that explanation is being given here. The current leaving the dot in any coil will produce an EMF, which is negative at the dot of the other coupled coil or positive at the other end of the dot. You can see any one. You can ignore this. You can ignore this. And if you can understand it, it is fine enough. Alright, so this is how we understand case 2. What is case 2? Current is entering the dot of coil 1. Current is leaving the dot of coil 2. That is case 2. Case 3. What is my case 3? Case 3 is similar to case 2. I have just swapped the two coils. What is it? I1 is leaving the dot of coil 1. I2 is entering the coil of coil 2, entering the dot of coil 2. Right? So in the previous case, I1 was entering the dot of coil 1, whereas I2 was leaving the dot of coil 2. Now I have reversed the situation. I1 is leaving the dot, I2 is entering the dot. But the situation is same. The same concept holds good. So you get a similar situation. If we can compare the two figures, they're just the same. They are just the same. This one and this one, both are same. Alright. In both the things we have minus positive. This is how the source appears in both the situations. It is the same thing. Alright. Now the other option that we have, current can leave the dots in both the coils. Instead of currents entering the dots, current may leave the dots in both the coils. That is also possible, right? That is also likely. That's also possible. So if the currents leave leave the dots or dotted ends of both the coils simultaneously, then we extend the same logic. If the currents leave the dot, then the dotted end is negative. So dotted end is below, so it's below, negative, positive. Here also dotted end is negative, below it is negative, positive. It is as simple as that. So this knowledge is helpful in dealing with coupled coils, and when we go on to write mesh equations in coupled coils, this knowledge becomes helpful. I have in fact taken up video. I have made videos on writing up of mesh equations in coupled circuits. There I have given a very brief introduction. So I was asked to give an elaborate content on mutually coupled coils, how to deal with dots. So I thought I would make this video. Hope this is helpful in understanding those lectures also, or those videos also. If you have any queries, again you can put it in my comment section so that I will be able to look into it and address the problems. Thanks for viewing. Your viewership matters to me. Thank you.